We're going to find a power series solution of a differential equation that, granted, we could solve using other techniques, but this will allow us to see what the process looks like. 4y prime plus y is equal to 0, and we're looking for a solution of the form y equals the sum as n goes from 0 to infinity c sub n x to the n. That's our power series. We're going to do what we do so many times in this course. Write down the form of solution y equals the sum as n goes from 0 to infinity of c sub n x to the n, and then plug it into the differential equation. A good thing about power series is that they all have power functions, and when we differentiate them, we get to use the power rule. Y prime is then equal to ncn x to the n minus 1 using the power rule on x. But now we have a bit of an intricacy that I need to talk about. Remember that the power series looks like c sub 0 plus c sub 1x plus c sub 2x squared, and so on. But we're talking about differentiating this. And the constant term c sub 0 will differentiate to 0. The first term is then c sub 1. So in order to reflect that we've taken this derivative, instead of the index starting at 0, we're going to start the index at n equals 1. And as a general rule of thumb, if our general term for a power series is x to the n, then every time we differentiate, the starting value for the index needs to increase. Plugging this into the differential equation, we get the sum as n goes from 1 to infinity of 4n c sub n x to the n minus 1. Remember, I'm going to put that 4 inside the sigma so I don't lose it. Plus the sum as n goes from 0 to infinity of c sub n x to the n is equal to 0. We're going to follow the same path we saw in the previous video. First, we're going to make exponents match, and then we need to make the indices match. Usually, in this case it won't be necessary, but generally we will. I have a x to the n minus 1 and an x to the n, and I'm going to make them both x to the k. We'll do them one at a time. The cosmetic change is that from x to the n minus 1 to x to the k, it looks like the exponent has increased by 1. It hasn't, we just have a different meaning for the variables. But I need to make that change across the board, right? So where I have c sub n, I need to have a c sub k plus 1. The change needs to go in the same direction, right? The exponent looked like it got bigger, the subscript looks like it gets bigger. Where I have 4n, I should have 4k plus 1, again, making it apparently 1 larger. And then the thing that makes this all legitimate is we offset those increases by 1 by decreasing the starting value for the index by 1. N goes from 0 to infinity. In the second sigma expression, we had x to the n. Nothing needs to really change except that n equals k, just to make everything match. So we have the sum as k goes from 0 to infinity, c sub k, x to the k. All of that is equal to 0. Since, whoops, I wrote down n equals 0, that should be k equals 0. Since our sigmas start at the same number and our x's have the same power, we can combine our sigma into a single expression here. And we get the sum as k goes from 0 to infinity of 4 times the quantity of k plus 1 c sub k plus 1 plus c sub k. All that times x to the k is equal to 0. Now, I said in the last video, we're really after what these coefficients are, the c's. If we were to expand out this sigma, we would have some coefficient, or I guess we'd have a constant term because it's k equals 0 and we have x to the k. Then we would have a linear term when k is equal to 1 with a coefficient. We would have a squared term when k is equal to 2 with a coefficient, and so on. But the right-hand side is equal to 0, which means that all of the coefficients for all of the powers of x are equal to 0. We can now go directly to 4 times the quantity of k plus 1 c sub k plus 1 plus c sub k is equal to 0. That's how I can express that all the coefficients are 0. At this point, what we have is a relationship between c sub k plus 1 and c sub k. And it's what we refer to as a recurrence relation. I'll write that down in a bit. But when we get to this point, we're always going to solve for the constant that has the highest subscript. What that means for us in this case is that we have c sub k plus 1 is equal to negative 1 over 4 times the quantity of k plus 1 c sub k. And then I want to note our starting value for the index was k equals 0. We're going to start plugging numbers in place of k, and noting that k equals 0 tells us where we need to start. So I'm going to include k equals 0 in the information. And I'm going to say that this equation that connects the c sub k with the c sub k plus 1, together with the starting, that's k equals 0, comma, 1, 2, etc. All of that together is what we call the recurrence relation. As far as I'm concerned, a recurrence relation is incomplete if you don't tell me the starting value for k. Why did we solve for the constant with the highest subscript? Because what we have now is a recursive formula. Once I know what a value is, c sub 1 for instance, then I can use this formula to generate c sub 2, and so on. We're going to start this work with k equals 0. When k equals 0, we have that c sub 1 is equal to negative 1/4 times c sub 0. We don't know what c sub 0 is, but it turns out that's going to be okay. This is as far as we can take this particular term, and so we're going to move on to the term where k is equal to 1. Then, if k is 1, c sub k plus 1 becomes c2. And then we have negative 1 over 4 times 1 plus 1. So that's negative 1 over 4 times 2, c sub 1. But we have c sub 1 in the previous term, so we can actually replace this c sub 1 using negative 1/4 c sub 0. The result is a positive 1 over 4 squared, we had two factors of 4, times 2 c sub 0. Moving on to k equals 2, that's going to give us a c sub 3 is equal to negative 1 over 4 times 3 c sub 2. Yeah, this is the game. We can replace c sub 2, and we end up with negative 1 over 4 cubed times 3 times 2 times c sub 0. I don't usually leave all this factored this way, like 4 cubed times 3 times 2, but I'm doing that this time because of where I know this is going to go. If we wanted to identify a pattern, we could say that in general, c sub n, a general term, is equal to negative 1 to the n. Notice that for c1, our term is negative. For c2, our term is positive. So for an odd subscript, we have a negative term, and for an even subscript, we have a positive term. We can achieve that by negative 1 to the n. And then we have a power of 4 in the denominator. The exponent matches the subscript on c, so we have 4 to the n. And then if you just kind of play this out a bit longer, you'll see that this 2 and then the 3 times 2, it's going to be represented by a factorial. It's n factorial. All that times c sub 0. Let's put this together now. We said that our power series solution should look like y equals c naught plus c1x plus c2x squared, and so on. And knowing that is more important as the chapter unfolds than being able to write down a general term with an n. So I'm a little bit out of order here. But knowing that y has this representation, this power series representation with the coefficients, we can say here that y is equal to, I have no information about c naught, so I'm just going to write it down as c sub 0. However, we know that c sub 1 is negative 1/4 times c sub 0. So I'm going to write down minus 1/4 c sub 0 x. I've replaced c1 in the x term. For c sub 2, we have this 1 over 4 squared times 2c naught. And I'll write it down in this case as 1 over 32 c sub 0, and that's the x squared term. For the x cubed term, we have negative 1 over 384 c sub 0 x cubed plus dot dot dot. Notice we have a c sub 0 in every term. So we're going to write this down with the c sub 0 factored out, 1 minus 1/4 x plus 1 over 32x squared. And at this point, I'm just going to put dot 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 there. Most of the answers that you're going to give in the rest of the chapter are going to look like this, some infinite sum with an ellipses. But when we see this c sub n, the general term, this leads us to y is equal to the sum as n goes from 0 to infinity of negative 1 to the n over 4 to the n times n factorial x to the n, with the c sub 0 factored out. And if you remember your power series, you'll know that this is c sub 0 times e to the negative x over 4. Don't expect a nice, tidy, closed form solution for most of what we're going to see in this chapter. I brought it to this point because if you wanted to check your answer, you could. 4y prime plus y equals 0 can be solved using an auxiliary equation. But believe me, most of the answers for the rest of the chapter, they're going to be this sum with this dot dot dot.